Structural Safety, GLOBE, Joint Committee on this Global Built Environment, GIF, Davos Global Risk Forum, Harbin Institute of Technology, HIT, Shanghai Jiao Tong University, and Marburg University. Actually, we around every 10 days, we have one speaker for one topic, and for each presentation, actually, we have broadcast on two platforms. The one is the Zoom. Now, all of you already here, and another one, I think, on Bilibili. Many of you also on that platform. And actually, if you want to discuss personally with the speakers, you're welcome to log in Zoom, because then you can discuss with the speaker directly. But on the Bilibili platform, you still can watch the broadcast videos. And also, we have a link on the official web page of this JCSS Joint Committee on Structural Safety. You can find easily on that, and you can find the link of this poster for each presentation, and also the link for recorded videos for past presentations. So you don't need to worry about miss something if you want, and also the contact information of us. Now, today we have the fifth talk by Professor Ming-Oh Yang, actually from Huazhong University of Science and Technology. On behalf of the organization committee, Professor Michael Faber, Professor Dagang Liu from Harbin Institute of Technology, Ming Liu and Dr. Weihen Zhang, and myself, I'm Jian Yunqing from Shanghai Jiao Tong University. We warmly welcome Professor Oh Yang to have the topic with the title Resilience and Sustainability Informed Design and Management for Infrastructure Systems. Before Professor Oh Yang's presentation, I would like to introduce him briefly. Actually, if you study or do some research on resilience, I'm sure you already have some. You already know this name because I believe that you already read his paper, one or more of them. Actually, Professor Oh Yang is currently a full professor in School of Artificial Intelligence and Automation in Huazhong University of Science and Technology. He published many papers on this resilience and sustainability, this topic. He now served as an editorial board member of 3 journals. So the first is ASCE Journal of Infrastructure Systems, IESS Reliability, Engineering and System Safety, and Resilience Findings. His research interests include critical infrastructure resilience, modeling and simulation of interdependent infrastructure, urban resilience, decision-making for resilience enhancement and uncertainty, and the urban science. Professor Oh Yang has published more than 50 peer-reviewed journal papers, and his publications have been cited more than 4,700 times, recorded in this Google Scholar, with this H-index reaches 28. He was actually among the most cited Chinese researchers in the field of safety, risk, reliability, and quality from years 2014 to 2019. And he is among the world's top 2% of scientists, a list released actually recently, annually, so by this Stanford University in 2020 and 2021. Yeah. Thank you, Professor Oh Yang. Now it's your time.
Okay, hello everyone. First, I think I need to thank Professor Faber and Professor Liu and Professor Chen and other 2 PhD students, the organization for this webinar, so that I have a chance to share our recent work with you. And today my topic is very huge, and I will just share some of my understanding and some of our previous studies related to this topic. In this topic, I will mainly focus on infrastructure system in cities. This is because of the curves shown in this figure. They display how the percentage of urban population evolved in the past several decades. With rapid urbanizations, more and more people move to cities. By the end of 2020, more than half of the population lived in cities at the global level. And this proportion will keep increasing and expected to surpass 60% in 2030 at the global level, which makes the future of our humans and the Earth tightly related to cities. It also means we have already entered the urban century. For the two terms, sustainability and resilience, and the sustainability usually refers to manage all resources and the enhance integration of all subsystems in ways that guarantee the well-being of current and future generations, ensuring distributional equity. While resilience is the capacity to maintain a certain level of functionality and to rapidly recover the normal operation in the face of internal and external disturbances. Sometimes in the literatures, these two terms are used interchangeably, resulting confusion. I quite agree with an explanation about the difference in a recent perspective paper in Nature Sustainability. To achieve high sustainable future, it needs to develop along a desired pathway, and the resilience can ensure the system evolve along this pathway. But if the developmental pathway is undesired, even the system is resilient enough, we may reach a low sustainable future. This means resilience is a necessary but insufficient condition to achieve high sustainability. So this talk will mainly discuss those resilience-based decision-making. In the context of cities and resilience, a natural raised question is, are cities resilient? The answer might be yes. This is because cities have proved to be remarkable resilient complex systems. Cities almost never die. And many cities have existed for thousands of years in face of natural and human-induced disasters. Maybe you can list some examples of cities that have died, but note that the vast majority persist. 70 years ago, atom bombs were dropped on 2 cities in Japan, but 30 years later, they were thriving again. Then, why this happens? Many empirical studies over the past 40 years points to that most urban properties vary continuously with population size and are well described mathematically on average by power scaling relations of the form like this. Here, y0 and beta are constant parameters. We can observe that the volume occupied by urban infrastructure per capita decrease in the form of sublinear scaling, with beta less than 1, with its average as 0.85, as shown in this left figure. And the rates of socio-economic quantities, such as wages and new inventions, increase per capita with city size in the form of superlinear scaling, with beta larger than 1 and its average as 1.15, as shown in this right figure. Briefly, this means doubling the population of any cities requires only about an 85% increase in infrastructure, but makes socio-economic outputs increase by 115%. This also means 50% savings in investment, but 50% additional increase in profits. So these scaling laws make cities even severely disrupted. They could be still recovered in some form. If cities are resilient, those infrastructure systems, including electricity, water, transportation, communication, and many others that form the backbone of cities should be also regarded as resilient. Then why we still care so much about resilience? One reason might be that we want more resilience. because rapid urbanization and technological innovation are improving our life standards, which make city dwellers expect more about the service quantities provided by utility companies. Despite the interrupted infrastructure services will be definitely recovered, citizens wish them return to normal operation as soon as possible. Another more important reason is that we are worried about the future due to the increasing complexity, which might be out of our control. This complexity is manifested in two aspects. One is the emergences of new risks due to rapid urbanization and the global environmental change. This makes the risks we're facing become more coupled and complicated, as shown in this figure. For example, extreme weather events might result in the occurrence of natural disasters, infectious disease, food crisis, climate action failures, and many other hazards. Another complexity is the increasing interdependencies among infrastructure systems and other subsystems in cities. Cities have multi-dimensional functionality, including the physical, economical, social, organizational, and environmental functionalities. These functionalities are tightly coupled. The functionality loss in one dimension will also impact the functionality in another dimension. Also, infrastructure system and other urban systems are interdependent in different scales, from the component level to single system level and to the integrated city levels. And to manage those systems, there also exist organizational interactions across different urban systems. Moreover, the interdependencies are also manifested at different stages. The pre-disaster mitigation strategies will affect emergency response and post-disaster recovery decisions, while post-disaster recovery will affect system capacity to cope with the next event. Any data to support this worry? Yes, we have. If we connect the long-term disaster-induced annual economic loss data, we can find that the annual economic loss caused by disaster in urban areas increase much faster than the urban population. This largely affects the developmental pathway towards high sustainability. Moreover, recall the above-mentioned scaling laws in cities. If we consider some liquid urban metrics, including crime, traffic congestion, and the incidence of certain disease, similar power law relations also exist. They all increase by 150% if doubling the populations. This means an additional increase of 50% when the city size increase. The good, the bad, and ugly comes together when a city grows. In summary, we want more resilience for high quality life standards, and we are extremely worried about the future due to increasing complexity of both hazards and urban systems, which together make the construction of resilient cities and resilient infrastructure systems in urgent need. Note that resilience is a concept in events, including natural disasters, public health emergencies, accidents, and social security incidents. For different types of events, the models used to assess resilience and those strategies applicable for resilience enhancement might be varied significantly. Next, I will first introduce the infrastructure resilience analysis in the face of natural hazards, because natural disaster caused the largest economic loss in the past. Taking the natural hazards in China as an example, for the seismic hazards, around 50% cities, 67% max cities are located in earthquake-prone areas. Since the year 1900, 35% earthquakes with magnitude larger than 7 occurred in China, causing 1 million deaths. For the flood hazards, around 62% of cities are in flood-prone areas, with big floods twice per year, resulting in 1,347 deaths and economic loss to $20 million per year. For the typhoon hazards, around 50% of cities are heavily affected, with 7 typhoons landing per year, resulting 443 deaths and the direct economic loss around $4.5 billion per year. For the geological disasters, around 40% cities are located in geological disaster-prone areas, with more than 10,000 events per year, resulting in more than 800 deaths and the direct economic loss around $0.8 billion per year. If taking all these losses together, the average annual economic loss in China due to natural disaster is around 430 billion in the unit of Chinese yuan and more than $60 billion. These are some clips in the movie San Andreas, which describe one truth in reality. When natural disaster, including earthquake, floods, hurricanes, or typhoons occur, they first disrupt some physical system in cities, including infrastructure system and buildings. So, urban resilience to natural disasters mainly depends on the resilience of infrastructure systems. Here, we use a set of figures to demonstrate how to assess the resilience of infrastructure system and natural hazards. It needs to first generate hazard scenario and then assess component damage state, compute system level functionality, and simulate post-disaster recovery. This map shows the results produced by each of these modules for the road, power, gas, water, and the artificial earthquake in a Chinese city, Zhejiang. In the seismic scenario generation module, we can get a spatial distribution of the seismic intensity with large difference across different sites in the study region. In the component damage states, this red indicates those components whose functionality has been compromised. In the system level functionality module, the green means normal operation. That means the functionality is not impacted. And the red means full loss of functionality. The rightmost feature shows the recovery processes of different infrastructure systems post-disasters. These 4 modules can provide a series of possible system functionality curves and the event in case of considering the uncertainty. To assess resilience, we should note that infrastructure systems actually serve different types of users. And these users are distributed heterogeneously in the space, including the residential, industrial, commercial, and some public facilities. More importantly, different users have different expectations on the functionality job and the recovery rapidity and the event. As we stated before, why we study resilience is because our humans or our users need more resilience, but different users have different expectations on the resilience. For example, for the residential users, the outage of electricity and water for several hours is acceptable. But for hospitals, it might result in the loss of life. Moreover, users expect integrated services provided by different infrastructure systems. If one system, such as power system, can recover very quickly, but another system, such as a water system, require a long time, then high resilient power system might be not very helpful. So we need to first determine the resilience goal of different users distributed in the study area, and then compare those simulated results from the above models with those resilience goals to calculate two resilience indicators. One is the robustly based indicators. which is the ratio of the simulated functionality job immediately after disaster to the expected functionality job. Another is the rapidity-based indicator, which is the ratio of the simulated recovery time to the expected recovery time. Based on these two indicators, we then can define what high resilience and low resilience should be. By using the above resilience metrics, these features shows the heterogeneous spatial distribution of the resilience level across the urban area. We can find that some areas, for example, in this area, they have high resilient power, gas, normal resilient water, but may have very low resilient road services. However, if we want a scalar form indicator of resilience, we can also use different weights to integrate the functionality levels at different critical time points post-disasters. Based on the concept of resilience from the perspective of system theory, the resilience assessment and analysis is a bottom-up process, and with the hazard generation first, followed by the modeling of physical components fragility and the physical system functionality job and recovery. After aggregating those damage and recovery information at the physical level, we can further analyze the social economic impacts, the environmental and organizational impacts. We can also identify those weaknesses in the organizational response for further improvement. We can on the contrary, the resilience enhancement and the planning is a up-bottom process, with the resilience goals set first, and then we need to make decisions at the component level. The objective function could be minimizing the investment budgets, with the resilience goals satisfied as the constraint, or minimizing the gap between the simulated and the expected resilience and limited budgets. Next, I will mainly introduce those decision-making methods to enhance resilience against natural hazards. One is the rapid recovery, which contributes a lot to the resilience levels. For post-disaster infrastructure system, their restoration processes usually include inspection, damage assessment, repair phases. This last repair phases usually takes the longest time and contributes the largest to the recovery rapidity. So we mainly focuses on this phase. And the question is how to determine the repair sequence of damaged components and limited budgets. And the performance of a repair sequence is judged by the resilience metric. For example, the resilience loss, which is one of the earliest metrics in the literature and is just a shaded area in this figure. Next, I will formulate the problem. For a geographically distributed infrastructure system, it can be described by a network with source and demand nodes. Each source node has a real output and capacity, and each demand node has a real demand and a target demand. Each line has a real flow and a capacity. All the real flow of components are decision variables manipulated by system operators, which can be modeled by some traditional operation model. After the disruption, there is a set of damaged components, such as node 2, 3, 4 in this case. As we focus on the repair phase, the repair time of each damaged node is known. The node state is described by X and T, which is 1 if it's normal and 0 if disrupted. Repair resources are characterized by repair teams, the time for inspection and assessment phases, and also the travel time between damaged components are much shorter than the repair time in the context of natural disasters, so they are ignored. Some assumptions are made for simplicity purpose. they can be renexed when applying the proposed model in practice. Based on this assumption and parameters, given a repair sequence, we then can get a system functionality recovery curve, as shown in this figure, with associated resilience loss 132. If using another repair sequence, for example, 2, 4, 3, we can get another functionality recovery curve with another resilience loss 80. This means that given a repair sequence, we can know the exact time when each damaged component is repaired. Given those time points where the system functionality changes, system operator can manipulate the component flow to minimize resilience loss. And this can be described by this linear programming mathematical model. Then the problem can be formulated to find a repair sequence. A sequence among all possible sequences to minimize the resilience loss or maximize the resilience. Many other variants of the Bar model can be similarly formulated in the case of considering the interdependencies between infrastructure systems and taking the repair time uncertainty into account. Details of these models are a bit complicated. Interesting audience can check our published papers for details. To solve these models, we propose several techniques, which are very helpful to efficiently solve them without sacrificing the solution quantity. The first is a period-by-period recovery using a selection method. This is motivated by the concept of resilience, which calls for the recovery of system functionality as soon as possible. So we divided the restoration horizon into smaller periods. And during each period, we identify a subset of damaged components to repair in the next time period by maximizing system functionality improvement. This can decouple the original problem into a series of smaller problems, with the computational cost significantly reduced. The second technique is the matrix-based resilience calculation method that can be applied to each time period when the solution space is not too large. It can fast calculate the resilience value and all possible repair sequences and output the best solution for those damaged components identified using the selection method demonstrated here. The third technique is the repair logic-based solution-based reduction methods. This is motivated by the fact that damaged components, as shown by the red icons in this figure, there are components in a network connecting the source and demand nodes. Because of these special locations, there exists a repair logic between those damaged components, which can be described by a repair logic network, as shown here. In this network, each damaged component can start to be repaired only if at least one of its labor nodes in this logic network has been repaired in higher priority. This technique can exclude some repair sequences that must not be the optimal solution, as they display the repair priority logic, leading to a significant reduction of the solution space. We applied the proposed algorithm and many other existing methods to several case systems. One application is the post-earthquake recovery of the electric power transmission system. The seismic magnitude is varied from 6 to 7 with a step of 0.5. For each seismic magnitude, 500 damage scenarios are generated. This table shows the average resilience loss over 500 damage scenarios at each seismic magnitude for different methods. The blue numbers are best solutions from all methods. The proposed methods perform the best in terms of solution accuracy and also the computational cost. Of course, the computational cost table is not shown here. Moreover, note that for the stochastic model considering the uncertainty, it can be solved by simply using the deterministic formulation, where the mean value of random parameters are used. And it can be also solved using a sampling-based technique by using a limited number of scenarios to approximate the estimation of the objective function. But this might cause insufficient capture of the uncertainty. Then a natural raised question is whether stochastic solutions solved from the sample-based approximation model perform better than the deterministic solutions. The answer is negative, and we found that in most instances, the stochastic solution solved using a limited number of scenarios is worse than the deterministic solution when judging the two solutions by a huge number of scenarios to sufficiently capture the uncertainty. However, it should be worthy to note that the differences are extremely small, less than 1%. As infrastructure systems are not isolated but independent, we also study how independent system resilience can be improved by sharing post-disaster damage information and making joint restoration. For comparison purpose, we consider 4 types of restoration strategies. One is the independent restoration strategy, where each system restores its damaged components individually to minimize the individual resilience loss. The second strategy is power first and gas second strategy, where damaged components are repaired with sequences to first minimize power system resilience loss. The third is gas first and power second strategies, where damaged components are repaired with sequences to first minimize gas system resilience loss. The final one is power and gas joint restoration strategy, where damaged components are repaired with sequences to minimize the resilience loss of the integrated systems. We find that compared with the independent restoration of each system, joint restoration-based decision-making can reduce the resilience loss by 30%. Another useful strategy to enhance the resilience is to make pre-disaster mitigation, such as hardening critical components, expand critical line capacity, and update network structure to increase redundancy. The component hardening strategy is one of the most frequently adopted strategies against natural disaster in both the literature and practice. It can be modeled in this way, using a decreased probability of component exceeding a damage limit state and a hazard scenario if this component is selected to be retrofitted. If we don't consider the uncertainty of post-disaster repair time of damaged components, a stochastic model can be formulated. If we consider the uncertainty of the post-disaster repair time of damaged components, a much more complicated model needs to be constructed. This is the detailed mathematical formulation of the resilience-driven component retrofitting model and the limited budget in the case of not considering the uncertainty of damaged components repair time. With the constraints grouped into 2 stages, the pre-disaster mitigation decision stage and post-disaster recovery decision stage. Solving such a model is really a huge challenge, as it needs to take a lot of uncertainties into account, including the hazard scenarios and component damage scenarios, and it also involves a lot of decision variables. Here, I just show the basic procedures to solve them. First, it needs to generate a certain pairs of component damage scenarios before retrofitting and after retrofitting, and they associate occurrence probability to establish a lookup table. Second, use these generated pairs of component damage scenarios to compute the resilience-based importance value of each component, and select a reduced set of candidate retrofitted components based on an enlarged budget. This step is motivated to reduce the solution space. After that, we can reformulate the problem as a deterministic problem with reduced solution space. And then we can use the L-shaped method to solve it. It can also repeat these three steps several times and to produce several solutions, and then select the best solution using large-scale Monte Carlo simulations based on the idea of sampling average approximation. Here we show the solution solved by proposed algorithms and other existing methods. This is a proposed algorithm. This is other methods. We can find that the proposed algorithm can give the best solutions, the least resilience loss, and also the computational time is significantly reduced compared with the conventional Monte Carlo simulation-based component importance-based methods. We have also compared those robustness, resilience, and economic loss-driven retrofit solutions and find that the resilience-driven solutions might be significantly beneficial. Compared with the robustness-based solutions, the resilience-driven solutions can reduce the economic loss by up to 30%. However, the resilience-driven solutions are very close to the economic loss-based solutions. This is because we found that these two performance measures are highly correlated, with the correlation coefficient larger than 0.99. We have also studied the resilience-driven retrofit strategy of the national railway system in China against the floods and find that compared with the component importance-based solutions in terms of network structure and the train flow, the solution from the proposed algorithm can enhance the resilience by 20 to 40. Recently, we also take the climate change into account and explore the resilience enhancement strategy to tropical, cyclone, blackout heat wave compound hazards. We find that in Harris County, the expected percentage of residents experiencing at least one longer than 5-day tropical cyclone blackout heat wave compound hazards in a 20-year period could increase dramatically by a factor of 23 over the 21st century. However, hardening 5% power distribution network can reduce the percentage of affected residents from 18.2% to 11.3%. Besides the natural hazards, the infrastructure system can be disrupted in a large variety of forms. Taking road networks as examples, they can be disrupted or interrupted due to debris flow, bridge collapse, traffic congestion, fire, explosive events, epidemic control measures, road collapse, tree breakdown, earthquake, floods, terrorist attacks, and many others. Instead of modeling this disruption one by one in details, enhancing the resilience to the worst-case disruption could be an alternative method. The worst-case disruption corresponds to the damage of critical components that can result in the largest system performance change, where the performance can be measured by resilience, robustness, economic loss, and many others. Moreover, worst-case disruption can simulate terrorist attacks, cyber attacks, which have high risk in the global risk map in terms of both the likelihood and consequence. Also, the worst-case disruption scenario can be also used in the robust optimization for resilience enhancement against natural disasters. From the perspective of resilience, maximizing system resilience and a given protection strategy and a given attack strategy can be described as a single-level defend model. Identify the worst-case attack strategy can be described as two-level attack-defend model, while deciding the best protection against the worst-case attack can be described as a three-level defend-attack-defend model. This is the mathematical formulation of the three-level resilience maximization model of interdependent infrastructure system against the worst-case disruption. The constraints include those related to resilience investment, attack capacity, geographical interdependencies, infrastructure operation, physical interdependencies, and nautical interdependencies. To solve such models, The basic idea is to decouple it into two problems. One is the master problem, which solves the optimum resilience strategies and the given attack strategies, and retain the lower bound of optimum resilience for the original problem. The other is the sub-problem, which solves the worst-case attack and the given resilience investment strategy, and retains the upper bound of the optimum resilience for the original problem. By solving these two problems repeatedly, we can solve the original problem. For single system, we show various locations of the three protected components, the blue dots. When at most three components, as shown by the red dots here, could be disrupted. This red dots shows the worst case disruption scenarios and the two best protection strategies. We also found that compared with the robustly-based protection solutions, the resilience-based protection solutions can reduce the system loss by up to 40%. For interdependent systems, we found that interdependencies largely affect the worst-case disruption scenarios, as shown by the red icons in these figures. This is for the interdependent system. This is for single power system, and then this is for single water system. We also know that many events in practice are manifested as localized disruption. For example, the control measures to contain the COVID-19, the explosive event occasionally occurred in cities, the terrorist attack, the inundation of roads due to low altitude and heavy rainstorms. By modeling those events as localized disruptive events covered by a boundary with a certain shape, such as circle, square, or urban administrative boundary, we have also studied a method to identify the worst-case localized disruption and also the best protection strategies to maximize system resilience. The resilience enhanced model is also a three-level defend, attack, defend model. We propose a maximum component set-based algorithm to solve it. By applying them to single and independent systems, we find that protecting a few critical components identified using our proposed approach can enhance system resilience against the worst-case localized disruption by 15 to 40%. As stated in the introduction section, there exist scaling laws between urban properties and city size. We take all the road narrows in the 363 prefectural level cities in mainland China as example to study the resilience patterns in the face of the worst-case localized disruption. The resilience is simply quantified as the post-disaster functionality level. And the functionality metric used here is the travel time-based accessibility. The required spatial population data are downloaded from the UN's Global Human Settlement Database. The network size ranges from a few hundreds to more than 6,500,000. Due to the large computational complexity, we also propose an algorithm to fast identify the worst-case localized disruption scenario to support the resilience calculation. Here we show the main findings. First, the worst-case disruption site tends to gather around the city center. And 62.3% cities have the worst-case disruption site less than 5 kilometers from the city center, as opposed to 14.3% cities have a site more than 15 kilometers away from the city center. Second, there exists a negative relationship between the city size and the worst-case resilience loss across all cities in mainland China, with the correlation coefficients as -0.8. For the spatial distribution patterns of the worst-case resilience across the whole country, we find that road networks in eastern cities are more resilient against the worst-case localized disruption, while those cities in western China have poor road network resilience. As at the nation scale, many natural disasters such as extreme rainfall maps and other events such as the city block for controlling the spreading of COVID-19 can be regarded as the interruption of infrastructure services in the whole city, which can be modeled as the city-level localized disruption with an impact in the national level. So we have also investigated the travel time-based resilience of multimodal nationwide transportation system in China and the city-level localized disruption, with the consideration of the timetable of trains and flights. This integrated transportation system includes the road networks with more than 4.2 million nodes, the high-speed rail network with 1,284 stations and 30,161 trains, and Iron Line network with 283 airports and 42,831 flights. We calculate the resilience of the integrated system and the localized disruption of each city, and found that Shanghai has the highest resilience loss with value as 0.77, while Nikuchu and Chengdu have the smallest resilience loss with a value smaller than 0.0001. Second, disruption of cities in the northern coastal China and the eastern coastal China result in significantly higher resilience loss than disruption of other cities. Third, well-developed cities with high GDP, more populations, and large transportation network tend to bring more resilience loss if they are disrupted. Conclusions. First, the average annual economic loss due to natural disasters is more than $60 billion, and it might exceed $70 billion if considering other types of disruption. Our study uncovered that pre-disaster mitigation and post-disaster recovery strategies can both reduce the loss by 30%. So, building the resilient cities have a large probability to reduce the whole loss by up to 30%. Moreover, in China, some cities have already developed the resilience management system against daily incidents. However, both hazards we're facing and urban system are becoming more complicated, with urban risks to extreme events significantly increased. So, incorporating the resilience management system against extreme events into existing resilience management system against daily incidents is in urgent need. This system should include hazard modeling, monitoring, resilience simulation, resilience analysis, resilience assessment, and resilience enhancement, resilience planning modules, with the consideration of country-specific, country-specific or city-specific disaster response organizations. That's it. Thank you.
Thank you, Professor Ouyang, for this very nice, actually amazing presentation. I think now it's a Q&A section, so any of us, if you have any questions, we are welcome to discuss directly with Professor Ouyang. I think it's quite interesting and useful presentation. As the host, okay, there's some. Can you see the chat box? Yeah, so there's some person from Switzerland, a risk and safety company. He asked if I understood correctly, Benjamin Schmidt, he asked if I understood correctly, the components infrastructure are modeled using fragility curves. How are these compiled for different components from different years of construction and maintenance condition? Further, is correlation considered among components or different extreme events? For example, pipelines are designed, built, and maintained by the same company. Storm surge and heavy rainfall in coastal areas occur simultaneously. Yes.
Yes, this is a good question. Actually, yeah. If we want to, because you know in the research, we usually use a simplified network for demonstrative purpose. But if you want to apply your model into practice, we need a lot of data because the number of components is huge. And we need the data to better predict the fragility of our model. So we need to connect data. I think that's the answer. If we don't have the data, we cannot do it. Maybe you can use some theoretical model and based on a few data to well predict the fragility. It's true that the fragility of different components are different, and it will degrade with the increase of years, and there are also correlations between components in the space. I agree with that, but to solve the problem, I think first we need data. Second, we need some better theoretical improvement.
Yeah,
that's it.
Yeah, thanks. I agree with that. I think, Professor Ouyang, may I ask you one thing? I thought it's interesting thing. You presented the concept or the idea about this sequential resilience. Resilience sequential decision making. In your consideration or your investigations, how do you think about how do you design this sequential, or how to make this sequential decision? Do you consider it's like when you take these solutions, find the solutions, do you use global optimization or local optimization? So you get the solution simultaneously for this sequence, or you get sequence one by one?
Yes, this is okay. This is also a very good question. Actually, we can formulate the problems as a whole, right? So we take all the pre-disaster and the post-disaster decision just at one time, make the decision at one time. But solve the problem is impossible because there are too many uncertainties. So the one way is to decouple it into different stages. You can make the decision at different stage. That will reduce the solution space. In our solution algorithms, we use the ideas. We don't make the decision just at one time, to make all the decisions, but make it separated into several smaller stages. And this will solve the problem very efficiently. And also because the resilience is a very interesting measures. It depends on the functionality functionality recovery rapidity, right? So if you can increase the functionality very fast in the beginning, the system will get a higher resilience. So if you decouple your problem into a few stages and use the functionality maximization as a alternative metric and a given time period, that will very efficiently solve the problem. So I think to solve such kind of problems, we need to consider what resilience is, and based on the idea of resilience and based on the resilience goals. If you take all this into consideration, the mathematical problems can be decoupled and make it more practical to other complicated scenarios, I think.
Yeah, it's clear, thanks. Any more questions from the audience? There's one question from our colleague. First, maybe we present Professor Luis. He say, how do you integrate the resilience management optimization strategies into city management system?
Wow. Okay. Okay. Let me go to here. Okay, thanks, Professor Lu. And this is a very interesting question. And we have some field investigation on some cities. And as I know, for the daily incidents, for the daily incidents. That means the disruption is small disruptions. The governments already have a very successful information system to fast deal with it. But for extreme events, they don't have. Why? Because they don't have the data. They have the data for infrastructure system, but they don't have the data for the hazards. This is one aspect. Another aspect, because for the extreme events, only one department in government cannot deal with it. They need different departments work together to cope with them. But how to make them cooperate together, this is another issue. So the key is to change the organization structure. But I don't know who will be responsible for that. This is not the challenge is not from the model itself. It's not from the theoretical part. It's from the practice part, I think.
Yeah. Yeah, thanks. There's another question from Ying Liu. Actually, she mentioned that your report is super interesting, and she found that in some cases the repair time lasts more than 100 days. And you have also introduced that there are different hazards or disturbances which will cause the failure of infrastructure. So during this long period, more than 100 days of this infrastructure recovery, if another hazardous disturbance event might happen, how could we consider its effect on the recovery time of the system? Yeah, I think that's interesting.
Yes. This is also very interesting. It's related to the hazard scenarios. That's what I mentioned here. You see, the everything is changed. The hazards, one hazard will need to the occurrence of another hazard. So the idea is that we need to take the scenario, the hazard scenario into account. If we have the scenario for the second hazards, and then we can incorporate them into one part, into one module of this stage, I think. For example, during the recovery process and maybe 10 days after another smaller earthquake happened, we can repeat these modules, right? This is the idea. But the problem is that how can we simulate the hazard scenarios, the multiple hazard scenarios? This is the big challenge, as I shown here. You see, one hazard will induce another hazard, right? So how can we simulate them? And the key is that if even you have a model, how to validate your model, how to make people trust you. So that's the key. Without data, we cannot convince others and also cannot convince ourselves, right?
Yeah. It's people always ask about things, how to validate. Yeah, it's true.
Yes,
yeah, thanks.
difficult.
There's another question from Professor Liu. Thanks. Professor Liu ask what's the main difference between robust-based, you mentioned robust-based and resilience-based optimization from the viewpoint of solution algorithm, yeah.
Okay. This is a great question. And for the robustness, and we don't consider the recovery process. And for the resilience, we need to consider the post-disaster recovery process. So if you only consider robustness, the model has much smaller decision variables. But if you take the resilience into account, there are much more decision variables because all the components flow at some critical time post-disaster should be all taken into account. So one difference is the model itself. The robustness model has smaller decision variables, while the resilience-based optimization has a lot of decision variables. Another difference is the solution techniques. Actually, if you can solve the robustly based model for a large network, for example, the 100 nodes. But for resilience based, you may only solve it for a very few scale, a small scale networks. For example, maybe less than 50. So the solution algorithm, of course, you can propose some heuristic algorithms and use the component importance based solution. But even so, the computational cost is significantly different, because if you calculate the robustness, you don't need to take the recovery percentage into account. While for the resilience, you need to take the functionality at a different time points post-disaster into account. So I think the main difference is the computation cost.
Okay, understand. Thank you. Thank you, William.
And may I add some extra question based on this your answer? So I understand there's a great computational problem. Do you have some advanced technology to solve them when you find that it's hard to calculate them in short time? Do you have some, or you just like some people I understand use like a GPU or something like this?
Actually, this is the direction we want to do, and you know, recently some people use the AI techniques to solve such kind of problem, right? So yeah, but I'm doubt about the efficiency. We are trying to prove that they are not efficient like our previous methods. So right now I cannot give you an answer because I need to check.
Yeah, thanks. Yeah, I understand. Yeah, thank you. Yeah. Any more questions from the audience? If you have any questions, you can ask. Yeah. That's the one. That's from Beijing Normal University. I think he mentions that. Thank you for your interesting presentation. I have some questions. How do you model complementarity and competitiveness in multimodal transportation systems? Do you consider the movement of passage flow in multiple systems?
Okay. This is also very interesting questions. And as I know, in the field of transportation engineering, they must consider the passenger flow, right? I think they must take the passenger flow into account. But in our model, we only consider accessibility. That means we only consider the effective travel time. So because if you take the passenger flow into account and without enough data, or the premise or the parameters are artificial, and it will and then the findings will be questionable. So currently we just take the accessibility into account. And even take the accessibility into account, the computation is also a huge challenge, really a huge challenge. For example, for the here. Yes, for the multimodal nationwide transportation scene, you see the network is very huge. And if you only calculate the accessibility, that means the travel time between any two nodes. And for such large networks, maybe it will need more than several months. So you see, just calculation of the functionality needs several months. If you want to tackle the resilience or the disruption and taking the uncertainty into account, it's impossible to get results. So you see, in the field of transportation engineering, and when they study the resilience, they usually use very small size networks. For example, maybe 10, 8, and the largest one in my mind maybe 20 or 30. Right? So if for large scale levels and considering all kinds of uncertainties, if you want to make the resilience based analysis and considering recovery and taking the capacity flow into account, that's almost impossible. Of course, you can formulate the problem, but if you cannot solve it, I think it might be useless.
Yeah.
Oh, let me see another question, right?
Yes.
So how to wow.
Yes.
Actually, I don't know how to give you an answer. I have to say that's my understanding about robustness and resilience, because in the general risk analysis, two famous professors, Evan and Hymes, and always have different ideas about these terms about robustness, risk, and resilience. So in our research group, we simply interpret the robustness as the performance job. You see, let me show you a figure to here. We just regard this is the robustness. The I is a robustness, and the I is robustness, and the resilience needs to take the whole recovery process into account, but I does not need to take the recovery process into account. That's it. So if you care about the exact definition or difference about the different terms, you'll be crazy, I think. I tend to do that several years ago, and I asked a famous professor, I want to do these things. He just ran away because he thinks it's useless. If you can differentiate them well, then you are right. Okay, but it seems scholars do not hold the same understanding from.
I have one more question. It's awesome. Are you considering disaster? There's a person, Sophia Rana. Are you considering disaster inequalities in your research towards disaster recovery and the resilience of cities or communities?
Yes, thank you, Professor Rana, right? This is what we want to do. We are trying to do that. You see, we have the resilience for different cities, right? Then the next is we use some metrics such as the Gini coefficients to measure the inequity. We want to do that. We have done that. You see, yes. the map show here. We have done that. But it's only limited. It's only limited to the localized disruption. Why? Because people don't care about because this disruption is simple to model. If for other natural hazards, we don't have data. I think even in US, they don't have enough data. So even they can get the results and get the resilience level for different cities, the answer may be questionable. So we only take the localized disruption into account, because then this kind of disruption is the definition is very clear.
Yes, thanks. I think that's clear. Any more questions?
Hello, Professor O, and you can hear me, right? I'm always very curious with the topic of the resilience of the whole city, because for the whole city system, we have so many structures, the buildings, the railway, the roads, the bridges, right? And there's so many infrastructure system, and so many different natural hazards like typhoons, earthquakes, like the ship impact, like these waves, all those natural disasters. And I'm very curious, how was the resilience of a single component defined? For example, for structure, for building, for bridge, the damage patterns are always different. how to define, or in another way, how to say or how to define whether a structure is still resilient or not under a certain disaster. And so many disasters, or they work together, how to define it? I'm always very curious because a city is such a big system, and I want to know something about that. Thanks a lot, Professor O.
Okay, thank you. Thanks for your interesting question. And this is actually a very interesting question in the very beginning of the resilience research. Some famous professors ask themselves and also ask us, what resilience is it? How can you define a system is resilient or not resilient? Right? How can you conclude one system is resilient and another system is not resilient? We can always find, for example, in this case, not here. For example, in the very beginning, we used the resilience laws, the shaded area, right? So we can always find another curve with the same shaded area. Can we say they are the same resilient? They always question themselves. And finally, I think the answer is that if you want to define it, it depends on here. You see, first, our city is resilient because they never die. Cities never die, then infrastructure system will never die. So infrastructure systems are also resilient. Maybe the infrastructure system in the future is not the physical one right now, but its functionality maintained, right? Because the city does not die. You see, so the key is that we want more resilience, but how resilient do you expect? It depends on the user's expectation. So we define whether a system is resilient or not using such a kind of the metrics table, I think. For example, for residential users, they have some expectation. For example, in 7 days after a certain type of earthquake, they hope the electricity will recover. And 30 days later, and 90% of the users could get the electricity back. So we need to define a goal. If you didn't define a goal, how can you define resilience? So the key is that if you want to solve the problem, you need to ask yourself, what do you want? Right? What resilience means from your perspective? That's the answers. And also for different types of hazards, you need to define different types of goals. So the answer depends on the users, not depends on the system. I think this is the key. Otherwise,
okay,
you
thanks,
always...
Professor. Yeah,
okay.
I understand somewhat. And in this way, I think, yeah, as you said, the different structure components are always coupled together. For example, the transportation systems will be very critical for this. For example, the time needed to recover, for example, the gas transportation or the electricity, for example. So probably can get some sensitivity analysis, which structural components will be the most critical for recovery of this structural resilience. Okay, thanks, Professor O. Yeah, I understand somewhat. Thanks.
Okay.
Thanks a lot. Yeah.
Any more questions? Yeah, I think we already 17 minutes more longer than scheduled, so we can stop now. Thank you very much for Professor Ouyang, and thank you all for coming. Yes, and you can find the recordings from the official JCS webpage as Wei Heng put in the chat box. You can find here, yes, to watch the video if you want to watch more, or if you don't want to miss something. Yes. Yes, thank you, Professor Ouyang.
Thank you all for the questions. And if you have any other questions, I'm very happy to discuss with you. Too many questions in this field. I think I'm really happy to discuss with you and maybe work work together to advance the field. Thank you very much.
Thanks. Thank you.
Thank you, William.
Okay, thank you.
Thank you.
Bye bye.
See you.